revolutionizing functional safety analysis with BLIPS. As technology advances, we rely on high-tech systems for safety and efficiency. At the same time, the high-tech industry tries to push the boundaries to innovate and commercialize faster. But with progress comes risks. Functional failures can lead to severe consequences. The drastic advancement in the technological sector requires bridging the significant gaps in the domain of design analysis. Firstly, current safety analyses are iterative, time-consuming, and resource-intensive. Most of the approaches are inductive, which means they propagate in the direction of effects from the causes. This approach becomes intractable for complex systems with a large number of potential initiating events. Predictions of failures largely depend on human experience and opinions, which are prone to overlooking potential causes or otherwise relying on extensive high-fidelity simulations that are not suitable at conceptual stages. This can lead to multiple design iterations, costing time and money for improvements and redesigns. Introducing BLIPS, transforming the approach to safety-critical designs with deductive analysis, also known as truth-preserving analysis. BLIPS is a formal method for deductive failure analysis addressing conceptual design early on in the design cycle. BLIPS allows multiple levels of abstraction for analysis, including, but not limited to, the functional level, component level, and at the deepest, physical variables level. The analysis begins with a high-level functional description of a conceptual system. Next, the component-level configuration of the system is developed, where the behaviors of the components are modeled using qualitative physics. After the functional and behavioral modeling is completed using propositional logic, and the interfaces among the levels of abstractions have been established, the next step is to begin failure propagation, initiating from a user-defined state of the system. This condition can include functional states, component states, process variables, or any combination of these parameters. The failure propagation identifies the failure trajectories and leads us to potential causes of failures by analyzing the entire state space of the system. Backward propagation with BLIPS allows propagation through the state space to identify the failure trajectories. During the propagation, the inference engine inherently determines the causal relationships among the nodes, where each node represents the component defined in terms of their behavioral model. Symbolic AI evaluates the validity of propagation at each node, proving or disproving possibilities as we progress. During the causal analysis, all the valid and the invalid causes for a given failure are recorded. Disproved nodes are eliminated, refining our analysis to focus on valid trajectories. After analysis, we obtain a backward propagated tree depicting an exhaustive list of failure trajectories. The extension of the tool, known as the probabilistic augmentation of BLIPS, utilizes a mathematical framework to assign weights to failure trajectories by employing a combination of probability theory and fuzzy logic. BLIPS can contribute to novel designs in various industries. In nuclear power, BLIPS can enhance the concept of safety by design by allowing early safety assessments, speed up analysis of self-driving cars, supporting robust designs in aerospace and aviation, optimizing biomedical equipment. Contrasting traditional regression with BLIPS can significantly improve the efficiency of safety analysis at an early design stage by identifying most of the faults before the testing phase. In addition to design safety, BLIPS also improves project economics and reduces time to market by improving the design cycle. Designers receive comprehensive insights, refining their innovative engineering solutions. In summary, BLIPS offers a formal method for deductive failure analysis, inherent determination of cause and effect, ability to generate an exhaustive list of failure trajectories, probabilistic insights into the results, applicability at early stages of the design, and obviating the need for computationally expensive high-fidelity simulation codes. Explore how BLIPS can transform your engineering analysis. We always welcome engagement and collaboration for advancement in science. Please bring your suggestions for working together. Thank you for joining us in exploring BLIPS. Let's innovate safely.